Take the cubed root of -1.
Take the cubed root of -1, or really the cubed root of both sides, but on the left-hand side it'll cancel with the cube. Give me the cubed root of -1. And like that is a final answer, that is an x value. Does it simplify? What is the cubed root of -1?
-1. So to compute the cubed root of -1, you ask yourself, what is a number whose cube is -1? Well, -1 times -1 times -1 is -1. That's not the main pointer today, but it's always nice to like absorb this sort of simplification thing. All right, here's another one. X cubed plus 2 equals -7. How would you solve that? Subtract 2 to the other side, giving me x cubed equals -9. Giving me a cube root of -9. Do you know a cube root for -9? No, but you can do something with the negative. All right, the cube root function is odd. If you picture its graph, it's got the symmetry that corresponds to odd, so you can factor out that negative. Cool, that feel good? Did that feel inefficient though? Do we like do the exact same walk twice in a row? Yeah, which is something that you would want to avoid. You want to avoid replicated effort. So, let's do it in abstract. Whenever you see a bunch of the same type of problem over and over again, instead of figuring out like a general strategy, abstract away all the differences. Solve the problem in abstract. And then whenever you want to solve a single instance of that problem, just use the fact that you've already done it in abstract. That looked like something we could solve for x. Yeah, for any given y value, you would subtract 2 to the other side, and then take the cube root. Subtract 2, x cubed equals y minus 2, so x is equal to the cube root of y minus 2. So what does that tell us? That tells us that if you ever see an equation of the form x squared plus 2 equals a number, its solution is x equals the cube root of that number minus 2. Oh, so now whenever you see an equation that looks like that, you can just solve it automatically. If you want to solve x cubed plus 2 equals 1, well, just plug that number in for y to get x equals the cube root of 1 minus 2, also known as -1. That feel okay? If you want to solve this equation, well, take that value, plug that in for y to get x equals the cube root of y -7 minus 2. And it simplifies, but that's not the point right now. If you wanted to solve that final equation, what does its solution look like?
Cube root of 18.
X equals the cube root of, it is 18, but I'm going to leave it as 20 minus 2, just for the sake of pattern recognition. Neato. That feel okay? So, this is the type of instance when you're interested in finding an inverse function. If you have a bunch of really similar equations that you want to solve for that variable x, you're probably interested in undoing this stuff that involves the x. That's what the inverse function does. So let's write down these, what is the inverse function. So whenever you solve an equation that looks like f of x equals y, to get x as a function of y, what you're doing is finding an inverse function to f of x. This new function is often denoted f inverse of y with a little -1 in the superscript for inverse. you should not interpret that as like 1 over f of y. It's f inverse of y. And as a remark, so in this expression, so that means that if f of x equals x cubed minus 2, then we found the inverse function to that thing. F inverse of y is the cube root of y minus 2. And here's the thing that's like just non-standard. It looks like the independent variable in that function is y. There's nothing wrong with that. But usually we want the independent variable to be x, because then like the horizontal axis is the x-axis. So a thing that we'll often do, we will swap the role of x and y when we want to find the inverse function. So instead of saying f inverse of y is the cube root of y minus 2, we'll say f inverse of x is the cube root of x minus 2. So let's see this in practice. Let's find an inverse function. Here is a function, f of x equals 3x minus 2. Let's find the inverse. And I'll follow these steps, and then we'll see if we could swap the order of them if we wanted to. So I will swap the variables x and y to turn this into the equation x equals 3y minus 2. That look like something you could solve for y? So I've taken the input value of x, I've renamed it y instead. And f of x is like the output value, so that's the y value. So I replace that y value with x. That look like an equation you could solve for y? By counting people I already have done. Cool. I'll pause for a moment. If anyone wants me to talk through the algebra of solving that for y, I can. Oh, cool, then I will. So, to solve for y, I want to undo everything that's on the y side of the equation. So it seems like a good first step. Add that 2 over. Let's add 2 to both sides. That'll give me x plus 2 equals 3y. What seems like a good idea next if I want to get y on its own? Nice. So that means, I'll write down the conclusion. The inverse to this function is x plus 2 divided by 3. That feel pretty okay? Nice. And the actual algebra wasn't the hard bit there, was it? So, as a quick remark, I did these 2 steps where first I swapped x and y, and then I solved for y. Would it be just as valid to do the following? Could I first take y equals 3x minus 2 and solve that for x, and then swap x and y? Would that also do the same job? Yeah, of course it would. So there's nothing magic about the order of when you decide to swap the rules of x and y. Just make sure you're solving for the right thing when you're solving. Does it matter what order you do the 2 steps? No. Also. Neato. Any questions people want to ask about this generic stuff before I flip over to the next page? Nice. So, I want to mention a weird subtlety that can happen. And I think I want to get to the subtlety by just trying to do something, and we'll see something weird happening. And I think I don't even like this water. I'm going to change this water. let's find the inverse function to f of x equals x squared, where fxn is supposed to be like an abbreviation for function. If you don't like it, you don't have to use that abbreviation. All right, so let's follow the same instructions. Let's swap the roles of x and y. That'll give me y squared equals x. And now I want to solve that for y. How would you solve that for y? Yeah.
Take the square root of both sides, but then you would have plus or minus y equals x.
Nice. So take the square root of both sides to get the square root off of the y side. Whenever you take a square root to undo a square, unless you already know that y like has to be positive or something, you get a plus or minus sign issue. All right, cool. Is there anything weird about that? Yeah.
It's not a function.
It's not a function. Why not?
It doesn't pass the vertical line.
Yeah, cool. So let's graph that. Y equals plus or minus root x. Well, I know what root x looks like. It looks like that. There's what negative root x looks like. It looks like that. And just so, it violates the vertical line test. And let's think about why it violated that vertical line test. Let's think about why that happened. So is it a function? No. So here's the cautionary note. Not all functions have inverses. And I think I'm going to come back and put a pink bullet point right there once I know what to put there. The pink bullet point that will go there will be telling me like what functions have inverses. And I guess here's like the problem that happened. If there are ever multiple x values that result in the same value for f of x, then the inverse to f of x will not be a function. And let's see that in terms of this picture. So there's the graph y equals x squared. And there's a single input, let's say 1. Oh, I'm sorry, yeah. There's a single output value, y equals 1. There are two different inputs that go to that output, namely 1 and minus 1. The inverse function now says that, well, f inverse of 1 should be the input that goes to 1. But there are two different inputs that go to 1, so f inverse has to be both of those things, but it can't be. If it is two different things, then f inverse is not a function. So whenever there are multiple input values which all result in the same output value, then the inverse isn't a thing. You can still like write down those instructions, you can even sketch a graph, but it is not a function. So I'll make up a word for that. So here's a bad thing. If there are multiple x values that go to the same value for f of x, then you don't have an inverse function. So that's a bad thing. A function is called one-to-one if every two distinct x values result in distinct values for f of x. So a function is called one-to-one if this previous sentence does not happen. So here's the reason to care about that, the connection to inverses. 1-to-1 functions have inverses. All right, cool. So let's do some quick checks for like, how can you tell if a function is one-to-one? So if you're being asked if a function is one-to-one, you're being asked if it's ever the case that two distinct inputs go to the same output. So let's look at like that leftmost graph, are there two distinct input values that both go to the same output value? Which two input values are you thinking of?
I see that -2, 0, and 2 all go to 0.
Nice. X equals -2, x equals 0, and x equals 2 all go to 0. So this function is not one-to-one. And that's enough. Like as soon as you find a single pair of inputs that both go to the same output, and we have 3 different ones that all go to the same output, you know the thing's not one-to-one. Are there another pair of inputs that go to the same output? Yeah. I mean, how about those 3 x values? Will they all go to the same input, the same output? Yeah. So there's lots of ways of telling you that this thing is not one-to-one. As soon as you find even 2 that go to the same output value, it's not one-to-one. How about the second function? Is it one-to-one? Yeah. Whenever you take 2 distinct input values, yeah, they both go to distinct output values. So this thing is one-to-one. And since it's one-to-one, it has an inverse function. Let's see what we can read off from the graph. Let's try to figure out what f inverse of 1 is by looking at that graph. So whenever you're asked what f inverse of a number is, I'm asking you, what is the input that goes to an output value of 1? I think it's worth writing that sentence. What input goes to an output of 1? And I don't know, by looking at that graph, what input goes to 1? Be approximate if you need.
1.3.
1.3-ish. All right, so how do you see that? You say, well, I want an output of 1, so that means I want y equals 1. I want to know what x value goes to it, so I want that x value. So it looks like f inverse of 1 is about 1.3-ish. And you can read it off of the graph from that. That feel pretty good? Nice. All right. So, motivated by this. So a function is not one-to-one if you can draw a horizontal line and it hits the graph in more than one point. Because the different points that it hits the graph in will give you different inputs that all go to the same output. The horizontal line test says that a function f is one-to-one if and only if so. It's an implication that goes both ways. If a function is one-to-one, then the thing after the if and only if is true. If the thing after the if and only if is true, then the function is one-to-one. So a function is one-to-one if and only if the graph of the function intersects every horizontal line in at most one point. That feel good? Nice. So, let's do some more graphical things with inverse functions. So, here's what's going to happen in this next exercise. It's going to go over 2 pages, and there's going to be some flipping back and forth. Here's the graph of a function. I'm going to have us study the graph of the inverse function, and we'll generate a graph of the inverse function on the next page. In order to sketch the graph of the inverse function, I want to start by just finding points that have to be on the graph of the inverse function. To do that, I'll need to evaluate the inverse function at some input values. And I'm going to try to be very careful and guided with my color coding now. So let's start with this. Let's try to compute f inverse of 3. To compute f inverse of 3, I need to know, by looking at this original function, this one, can you find an input value that results in an output value of 3? What input value were you thinking of? I hear some 2s being whispered. People agree?
Negative 2, negative 2. See, I'm looking out at you and you whispered, so I didn't hear the negative. I'm not looking at the graph. Nice. So, x equals negative 2. Coming from like this point, I guess. So, that means f inverse of 3 is negative 2. So if I want to graph the inverse function, what point must be on the graph of y equals f inverse of x? Well, it'll be input of 3, output of negative 2. That seem pretty okay? Nice. Let's graph that on the next page. 3, negative 2. 1, 2, 3, negative 2. Now, let's just do that same thing like 3 more times. So I think I'll do it one more time with some guidance, and then I'll let you do the remaining 2. So let's try to compute f inverse of 1. So to do that, I want to know what x value goes to 1. So I want to know the x value that goes to 1. So that means I want to start with a y value of 1. I want to see the point where it hits the graph. That's this red point. And what x value is that? Negative 1. So, what's f inverse of 1? It's that x value, it's negative 1. Nice. Let's plot that on the next page. So that means negative plus 1, comma, minus 1 is on y equals f inverse of x. Negative 1, 1 becomes the point 1, negative 1. So far, so good? All right. So now, I'll flip back over here. Follow those same ideas. Determine f inverse of 0 and f inverse of negative 3. So, what is f inverse of 0? I hear a 1. Do I hear a second for 1? Do I hear a call to discuss? Cool, let's discuss. So, I agree. F inverse of 0 is 1. Why is f inverse of 0 equal to 1? Well, let's think about what the inverse function means. When I want to compute f inverse of 0, that means I want to know what input does this function send to 0. So I'm interested in an output value of 0 for this function. So output value is y value. So I'll think about y equals 0. What is the x value you see on this graph where with that has y equals 0? 1. So, you know that f of 1 equals 0. So, f inverse of 0 equals 1. Inverse functions swap the role of input and output. So, graph that on the next page. X equals 0, y equals 1 is a point on the graph of the inverse. 0, comma 1. Nice. All right. So same question one last time. What is f inverse of -3? Yeah.
2.
Are you R2? People agree? Nice. I guess that's because of this point. Cool. So you can read off inverse function values by looking at a graph. If I give you a thing I want you to plug into the inverse function, and I give you the original graph, figure out what x value goes to the y value that's inside the inverse function. Cool. And the original function is very like straight liney between those points, so I'll use straight lines for the inverse function as well. Groovy. So there's the graph of the inverse. And let's just see if we can recognize some features of these two graphs. I don't know. How do those two graphs compare to each other? Let's maybe even like think about the color coding. So, oh, I used a different purple for the two purples. So those two purple points, how do they compare? Yeah, but what do you mean by inverses? Yeah, the coordinates just got swapped. So when you graph the inverse function, it looks like maybe you just swapped the x and y values on the graph. And let's see, does that agree with the other color-coded points? X and y values swapped? In fact, that's just generally true. If you have the graph of a function, then you can get the graph of the inverse function by swapping x and y values. And maybe I'll say this one other way. So just like how one of I talked about, like if you have the graph of f of x, how do you get the graph of f of negative x? You like reflect over the y-axis, or you just put a negative sign in front of all of the x coordinates. Same thing here. So there's like the what to do to addresses thing. You can also do this by reflection. You can get that by reflecting over the line y equals x. And let's just see if that actually walks out. So there's this point at 0, 1. You reflect it over the line y equals x, you seem to get to the point 1, 0. Is that the point where you should go? Yeah, it looks like the x and y values just got swapped. So that orange is now like another more geometric sounding way of swapping the x and y values. Neato. So, I am going to take a moment soon and curate what I have in Desmos. The next thing I want to do is I want to talk about finding an inverse function algebraically. There's a function, f of x equals x minus 1 over x minus 2. Yeah.
So, I'm sorry, it's reflected over which axis?
Not an axis at all. The line y equals x.
Oh, okay, okay.
Yeah. So you reflect over an axis when you want like negative f of x or f of negative x.
That's why you do that one time, okay.
Yeah.
Got it.
Awesome.
Got it.
Everything's coming together. All right. So let's try to find the inverse to this function. And you know what? Let's do something a few different ways. Let's think graphically. I'm going to modify something in Desmos to avoid revealing like an answer prematurely. Cool. Okay. We're back. So there's the graph of this original function that I want to find the inverse to algebraically. We will in a moment. Before I do that, I want to see the graph of the inverse function without having to find the formula for the inverse function. So what's the inverse function? I just want to swap all the x and y values. Desmos is perfectly happy to swap the role of the x and y variables. If I want to find the inverse to this function, there's what its graph will look like. That feel pretty okay? Nice. So I know what the graph's going to look like. I'm going to use that to check the algebra that we'll do in a moment. So, back to the paper. If I want to find an inverse to that function, what's the equation I need to solve? What's the equation I should write down?
X equals y minus 1 over y minus 2.
Nice. I'm going to take this, I'm going to swap the role of x and y, where I'm thinking of that as a y. X equals y minus 1 over y minus 2. And I want to solve for y.
And maybe I'll see a show of hands in terms of how people feel. How do people feel as that's something that they're able to go through all the motions of solving right now on their own? Cool. How many people want me to do some talking about solving this? Nice. Then, those of you who want to do it on your own will probably be done long before I am. In fact, might be done already. So you want to solve this for y. And it looks like there's not an obvious, there's not something you could do to just get y on its own all at once. So instead, let's look on the side that has the y's, and look at the thing that makes it most complicated. It's complicated because there's some division on that side. So how can I rewrite this equation so there's not division on that side? Yeah.
Multiply both sides by its denominator.
Multiply both sides by the denominator. Which maybe I used the word cross multiply for this last time. Let's cross multiply.
That will give me x multiplied by y minus 2 equals y minus 1.
And those parentheses are important because I want all of the denominator to be multiplied by the left-hand side of the equation. All right, what next? What seems useful to do next?
Distribute the x.
Let's distribute the x. I think that's a reasonable thing to do because what's an overarching game plan? I'll want to get all the y's onto the same side, all the non-y's onto the other side, and then at least all the y's will be on the same side. But before I do that, I see an x times y and a 2 times x. I don't want to move the 2 times x over. So let's distribute.
Distribute xy minus 2x equals y minus 1.
Cool. So that's, even if you don't have much motivation, that's still an improvement. It's annoying that the y is in the parentheses on the that-hand side. Now the y isn't in the parentheses anymore. That makes it less annoying. All right, what next?
Subtract y.
Let's subtract y.
And I think I'm going to, as long as we're subtracting y from both sides, I'm also going to add 2x to both sides.
Right, get all the y's onto one side, get all of the non-y's onto the other side.
All right, so xy minus y equals 2x minus 1.
Did I perform that step correctly? Cool, nice. That's looking nicer, and that now at least all the y's are on the same side. So what should I do next? That'll make this piece complicated though. If you divide everything in sight by x, I'm taking advantage of erasable pen, so I'm going to write down that instruction, and then we'll see that something not useful happens.
So if you divide both sides by x, sure, this side's 2x minus x. I see just a y because those two will cancel. Oh, but I'm stuck with this y over x term. That's annoying. So I don't want to do that. And like, it's not that that's an illegal step or anything, it's just a step that will wind up not being helpful. Yeah,
Factor out a y from the left side, like
awesome. So
y.
it would be really helpful to know exactly what the thing is in front of y on the side with the y's. And I do see an x times y, but I also see this minus y. So let's factor out the y, then I'll see a number multiplied by y, then I'll know what to divide by.
x minus 1, y equals 2x minus 1. In this step, we have factored.
All right. So now that we know what number is actually multiplied by y, namely x minus 1, what should we do next? Oh, cool. Does that do it? Does that get y on its own? Awesome.
So, let's write down a conclusion.
And you know what? As long as we have this graph pulled up, let's use that. I'm going to go back to Desmos, and I am going to graph the thing we just found. 2x minus 1 divided by x minus 1. Does that look like it agrees with the blue graph that we said was the graph of the inverse? Nice. All right. So we have the inverse to this function. Yeah, with the time we have left, there's enough time to do this. Let's talk about domains and range. So we have this nice interaction between graphs of a function and graph of the inverse. If you want the graph of the inverse function, you swap all the x and y values. Let's see what that does to domains and range by reminding ourselves how you read domain and range from a graph. So forget about the function that we just walked with for now. Just if I give you a graph of a function, how do you read the domain of that function from the graph? Yeah.
I can x min comma x max.
Oh, sure. If the domain happens to be an interval, then yeah.
Yeah.
But in general, it's just like whatever all the x values are.
Yeah.
Right? Conceivably, maybe we'll even see that one. Like the domain of that function isn't x min to x max. It's negative infinity to where that vertical asymptote is. Domain of a function, just all the x values you see on a graph. What about the range of a function? And maybe you see on the graph is the wrong wording. It's all of the y values that are on the graph, regardless of whether or not you see them. Now, the graph of a function and the inverse function differ just by swapping x and y coordinates. And let's think about what that does to domain and range. So suppose you want the domain of an inverse function. So that'll be like all the x values on the graph of the inverse function. Ooh, but that'll be the same as the set of all of the y values on the graph of the original function, right? What's the set of all the y values on the graph of the original function? What's another word for that? If I give you a function and ask you for all the y values, what am I asking you for? Yeah, the range is the font I was going for. But let's just write down the conclusion. If you want the domain of an inverse function, it's the same as the range
of the original function. With the logic being, the domain of the inverse function you can read off from the graph. So imagine you graphed the inverse function. You would then read off all the x values you saw. But you already know what those x values are. They're the same as all of the y values you would see on the graph of the original function. And that's the range of the original function. And the same thing is true the opposite way too. If you want the range of the inverse function, that's the same thing as the domain of f of x. And with the time we have, let's see if that actually holds up. So I don't know if I'm going to spend time filling in the blanks of the stuff on the next page, but let's see if this actually walks out correctly. Well, no, maybe this is fine. Let's pull up the graph. So for f of x equals x minus 1 over x minus 2, we got f inverse of x equals 2x minus 1 over x minus 1. So let's just hold on to that off to the side. So for x minus 1 over x minus 2, what's the only thing not in the domain of this function? 2, right? Because that gives you division by 0. If you inspect the graph of this original function, maybe you believe that the only thing not in the range is the location of that horizontal asymptote. That seem believable from the graph? Nice. Where's the horizontal asymptote of that thing? 1. So y equals 1 is the only thing not in the range. And if the thing we just said is correct, then for the inverse function, those two facts should just swap. And let's see if it does, in fact, just swap. So there's the formula for the inverse function. What's the only thing not in the domain of that thing? 1. Plugging in 1 results in division by 0. The only thing not in the range of this thing is the location of the horizontal asymptote. Where's the horizontal asymptote of this thing? 2, right? It's the they're both degree 1, so it has a horizontal asymptote. To get the horizontal asymptote, you just look at the leading term, you get 2. Oh, neat. So they just swapped. The place where the thing not in the domain became the thing not in the range. The thing not in the range became the thing not in the domain. And let me close with an incomplete discussion of the first thing that we'll do next time. So, the full-blown, maximally technical mathematical definition of an inverse function is as follows. If you have a one-to-one function f of x, then the inverse function f inverse of x is the unique function which satisfies that f inverse of f of x is equal to x for every x in the domain of f. And f of f inverse of x is equal to x for every x in the domain of f inverse of x. And does that seem sensible for what the inverse function should do? So you take an input, you do f to it, and you get an output. And then f inverse just undoes that and sends you back to x. And the opposite also happens. If you start with a value x, and you undo all of the instructions for f, and then you do all of the instructions for f, you'll get back to x also. So there's a full-blown, maximally mathematical definition of the inverse function. If you now have something you think is the inverse function, which we've just found an inverse function, you can verify it's the inverse function by checking that these two identities happen. And that's what we'll do at the start of next time. And inconveniently, that is also exactly the homework assigned for today. So maybe don't look at the open-ended homework for today just yet. We'll do it first thing on Wednesday. We'll discuss it. Yeah. And let's see,